everyone. Today we're going to take a further look at what we talked about last day for scatter plots. And we talked about that you can still see a pattern or a trend happening. Now we're going to take an even closer look at that. So even though we don't have an exact trend, we can use the data that we have to come up with an equation that best fits that data. And that's what we're doing when we're trying to figure out the regression line of best fit. So we're going to use Desmos to tell us what the equation that best fits that data. Going to draw a line in there, give us the equation so that we can use the equation to approximate what we need to know from that data. And we can make predictions based on the data. So example number 1, hours worked versus income. Is there a causal relationship? So does the number of hours worked cause an effect on the income? Well, obviously here, yes. Okay, the more hours you work, the more money you're going to get paid. So that tells us that we have a positive correlation. So as number of hours worked increases, so does income. So we're going to use Desmos to create a scatter plot of income versus hours worked. And I've already put this on a scatter plot. Don't forget that you just click on your plus button over here to pick a table, fill in your table of values, and you can change your axes with your wrench over on the right hand side. I have set my axes to 0 to 45 and 0 to, and I put actually 400 in here. So Desmos sometimes is going to alter your numbers a little bit without changing the fact that you can see all of your points. So we can see the graph here, and I've labeled our axes, number of hours on the bottom, earnings on the side. For Desmos to give us an equation of the line of best fit, remember for a linear equation, our general equation is y equals mx plus b, where m is our slope and b is our y-intercept. Well, that's what we're going to ask Desmos to tell us. So we're going to put it in here, but we're going to put it in an approximate way. And what we want to do is make sure that we're going to put it in here y1. Notice that we have y1 up on the top here. That's what our y-axis is labeled as, so we have to specify that, y1. Next, we're going to put our approximate sign in. And if you click on the ABC here, you'll notice at the bottom, we have our approximate sign. So we're going to put that in there. And we're also going to put our MX1. So we also have to put a 1 in there to say we're pulling from above from list 1, and plus B. So you'll notice that our information is down here for what our slope is and what our y-intercept are. So our slope under M here is 8.4. Now the y-intercept, notice that to the negative 15 means 15 decimals to the left. So it is so negligible, we are rounding it to 0. That value with 14 zeros is basically 0. So our equation for this is y equals 8.4x plus 0. Okay, so we created our scatter plot. We're now going to record our equation, subbing into the formula. So earnings is equal to 840x. Notice that means that our slope, $8.40 per hour. And if we don't have any hours worked, we get nothing, is our plus 0 at the end, our y-intercept. Now determine the number of hours worked to earn 310.80. Well, that's our earnings. So that's going to go over where y is. And now we're basically just going to divide both sides by $8.40. And when we do that, we see that 37 hours worked earns $310.80. Okay, so even though we don't have an exact relationship, we can still, well, this one is exact. Now, the other thing I want you to notice as well, when we take a look at this again, there's an R value. So under our y1 is approximately equal to mx1 plus b, we see R equals 1. This is what is called our correlation coefficient. And this tells us how well our data fits our line. And notice that in this case, our R value is 1 because every single piece of that data is on the line. It is an exact relationship. So we do know for sure that this person makes $8.40 an hour. It doesn't vary. It is an exact relationship, very strong relationship or a very strong correlation. And the R equals 1 tells us that. Okay, it is exact. If we want to go back here and we're going to talk about exactly that. So when the equation of the line of best fit shows, you'll also notice the value for R. And notice we're ignoring R squared. That's for a quadratic function. We're not working with quadratics here. So we have our correlation coefficient. And as we said, if the data fits exactly, if it's a positive correlation, R will be 1. If it's a negative correlation, R will be -1. Okay, so if our data falls to the right, the correlation will be negative and we'll have a value of -1 if it is exact. So if our value is, close to 1, very close to 1, or something like 0.94, it is very strong. If it falls to about 0.75 or -0.75 in the case of a negative, it's going to be somewhat strong. Okay, or we can just call that strong. Once we fall to 0.7 or -0.7, we're getting a little bit weaker. And 0.04 or -0.4 are considered very weak. And if there's no correlation, then our R value will be close to 0. The closer to 0, the more random the information is. So example number 2, this time we're going to look at weeks, dieting, and mass. So again, we're going to plot these on a scatter plot. And when we do this, again, I've got my data already on my scatter plot, and I'm going to go down to and input my y1 is equal to approximately mx1 plus b. And again, we can see that our equation, and we're going to round to 2 decimal places, so our slope is -1.21, y-intercept 66.73. We're going to sub those into our equation. And again, notice as well, we're also going to take notice of our R value. Notice our R value is -0.97. So this is a strong relationship. Okay, it's still very strong. And we notice that some of our points are not on the line, which explains that it's not, our R value is not -1. And again, it's a negative correlation. So our R value is negative. So let's take this back to our question. So are the variables positively correlated, negatively? And there is a negative correlation. As number of weeks dieting increases, mass decreases, and there is a causal relationship. So dieting causes an effect on the mass. So our equation of our line of best fit was -1, y equals -1.21x plus 66.73. And our R value was -0.97. So this is a strong negative correlation. And we can even say very strong correlation. Those variables are strongly correlated. Now, estimating the mass after 15 weeks of dieting, we're just subbing in 15 for x. And when we find that answer, we get 48.58 kilograms. Okay, and we would do our therefore statement. Mass after 15 weeks is approximately, okay, and again, we're still approximating, using the information that we have. Now, estimating the number of weeks dieting required to have a mass of 48, we notice that that's pretty close. So we're going to be able to check our answer once we sub this in here. 48 is our answer for y. So we're going to have 48 equals -1.21x plus 66.73. When we subtract 66.73 on the other side, we get -18.73. And then we're going to divide both sides by -1.21. And when we do that, we get 15.5, which makes sense. We said 15, it's just a little above 48. So mass is approximately 48 kilograms in the 16th week. Okay, so we didn't quite hit it at 15. It'll happen during the 16th week. Okay, so again, just to give you an idea of how we can still use those scatter plots to still predict what's going to happen in the future.